Hi, this is Mr. Ye. So today I would like to go over all the exponential rules. First, so we're going to go to something called product rule, quotient rule, zero power rules, and negative exponent rule, and the power rules. Okay, so if you have this 5 rule, and the last one is I'm going to go over something called definition radicals. So 6. I think this should be part of the exponential rule because it's called rational exponents. It's a to the m over n power is equal to the n roots of a to the m. Okay, so that's something that I think if we're gonna do it everything together. So let's start with the first rule, and we're gonna talk about the first example. Example for the a to the m times a to the n equal to a to the m plus n. This is called product rule, and we have something that is very common in use. Like for example, if I have 2 to the second power times 2 to the fifth power, I mean I can do the slow motion math, which is I can multiply those 2 squared times 2 fifths, I can rewrite it this. So that's equal to 1, 2, 3, 4, 5, 6, 7. So this is the exponent, this is the base. But the only requirement is this, make very clearly that it's 2 squared and 2 fifths. Now this one, need to make sure that they have the same base. If they're same base, that's going to multiply together and get 2 to the 7th power. So that is one thing that students tended to do. It just write it this way and then just say 2 to the 7, but that's too much work. What if I say 2 to the 30 times 2 to the 15? Do I really want to write out 2 to the 30 times? 2 to the 15 times. You know this multiplying, so do they have the same base? That's the question you have to ask yourself. Do they have the same base? So same. So they both have 2, or they both have x. Then you say, okay, well, according to the exponential rule, it's going to be 30 plus 15. That's equal to 2 to the 45. So that was the product rule example. Okay. So anybody can do this. So, and let's work with the x. So x to the 5 times x to the 7. That's x to the 5 plus 7. That's equal to x to the 12. That's the exponential rule. Product rule. Okay. So we're going to change this to product rule example. And then we're going to do a quotient rule example. Examples. So a perfect example would be 2 to the 5th over 2 to the 2. But if I do a slow motion like this, which takes forever to do, I usually prefer not to do that. So I'm going to erase this part. I'm going to do it in this marker. So it'll be 2 to the 5th over 2 to the 2nd. That's equal to 2 to the 5 minus 2. That's equal to 2 to the 3. But some people prefer to do it this way, which is take too long. Because if you really want to write out like this, it's 2 to the 3rd, this is not a good way. This is an efficient way. Imagine if you have 2 to the 64 over 2 to the 32. That's 2 to the 64 minus 32. That's equal to 2 to the 32. So top minus bottom. And stay at the top. So there's still 1 on the bottom. So top minus bottom, stay on the numerator. Even the numerator could be negative. You can stay up there and you can change with other rules. So you can practice like say x to the 17 power over x to the 12 power. Do they have the same base? They do. If it's x, this is a y, then they cannot subtract. But they both are x to the 17 power, x to the 12 power. They have to be the same thing, so it'll be x to the 17 minus 12. That's equal to x to the 5th. So that is the quotient rule. Now the next thing we're going to talk about the zero power rule. So these two, we already practiced. We're going to put everything together. So what is zero power rule? So zero power rule, it just says anything to the 0 is equal to 1. So for example, 3 to the 0 is 1. Negative 3 to the 0 is 1. Be careful the next one though. Negative 3 to the 0 power. Well, this one you have to be careful. This one's 3 to the 0, so anything to the 0 power is 1, right? So this is a parenthesis right here, invisible, but it's there. 3 to the 0 is 1. This is negative 3, so anything to the 0 power is 1. Now here, you got to be careful because there's no parenthesis. There's no parenthesis, that means exponential is going to go first. Exponent rule is going to go first. So 3 to the 0 is 1. But it's going to times by negative sign. So technically this has happened. 3 to the 0 is 1. So negative 1. So the answer is negative 1. So this last part, a lot of people get confused. Okay, so since we talked about zero exponential rule, so we're going to talk about that. We're also going to talk about a proof. We're going to prove 3 and 4 at the same time. And this proof is very interesting proof. A lot of students don't understand why is anything to the 0 power 1? It doesn't make sense. How do you do to the 0 power? And how does, like, for example, another question is like, why anything to the 0 power, anything to 0 power 1? Why? We always ask the teacher, and teacher just say, hey, just memorize it. But if you memorize it without knowing why, what's the point? Because next day you're gonna forget. Okay, and how about 0 to the 0 power? So why? And how about 0 to the 0 power? Why is that equal to 1? That doesn't even make sense. So you have to think about why. Now we just start with why is anything to the 0 power is equal to 1? We're going to do a simple proof, this pattern proof. So 2 to the 4th is 2 times 2 times 2 times 2. That's equal to 16. We know that. 2 to the 3rd power is equal to 2 times 2 times 2. That's equal to 8. 2 to the 2nd power equal to 2 times 2. That's equal to 4. 2 to the 1st power is equal to 2. Now if you realize this 4, 3, 2, 1, they have to follow the same pattern. So it's going down each by 1. How about the answers here? If you're going from here to here, you see times by 1/2. Because divided by 2, same thing is times 1/2. The reason why I do times 1/2 is going to help me with negative exponent rule. If I have here, it's going to be times 1/2. And here it's going to be times 1/2. And if you go from here to here, it's going to be times 1/2. So what's 4 times 1/2? Well, 4 times 1/2 is going to be 2. Now it concludes that 2 to the 0 power, or anything, you can replace this with any number. So 2 to the 0 power, when you're going from here to here, is going to times 1/2. So therefore, it's equal to 1. And like what other people says, why is that 0 power is 1? what does 2 to the 0 power really look like? Well, that's what it look like in a pattern way. Now, we just proved number 3, but 0 to the 0 power, that's another question. Why 0 power? This is even hard to imagine. So this one, we actually had to use something called limit process. So we're going to use 1 to the 1 power as 1, 0.9 to the 0.9. Okay, so what we're going to do is we're going to get a calculator, and we're going to work it out. So I have this fancy calculator. So we're going to use something called a limit process to get there. 0.9 to the 0.9 power, that's equal to 0.9095. So this star already doesn't make sense. Why 0 to the 0 power is going to be 1? You start with 1 to the 1 power is equal to 1. 0.9 to the 0.9 power, use a pattern. That's going to be 0.9095. And then you say, what is 0.8 to the 0.8 power? Or 0.8 to the 0.8 power? That's equal to 0.8365. And then 0.7 to the 0.7 power is equal to 0.7790. So according to this trend, if I'm going toward 0, 0.7, so 0.5 to 0.5 power, 0.4 to 0.4 power, this trend is going what? To close to 0. But we say 0 to the 0 power is a question mark. According to the teacher says, that's equal to 1. But at here, the path doesn't look that way. But we're just going to keep on going. So we're going to use the limit process to keep on looking. So that's 0.6 to the 0.6 power. So that's 0.7360. We're going to keep on going. 0.5 to the 0.5 power. That's equal to 0.7071. Now, if you come and pay attention to here, now some smart student good at math then can say, well, the number is actually slowing down. But nonetheless, it's still going toward 0 to the 0 power is equal to 0. But it's slowing down though. So we're going to keep on looking, keep on observing this. 0.4 to 0.4 power. So 0.4 to the 0.4 power, that's equal to 0.69313. It's getting smaller, but smaller increase. So now this is the thing that we're going to use to, we're going to say, wow, this is interesting. 0.3 times 0.3 is equal to 0.6968. Now, do you realize they take a turn, which is kind of, you feel like math is broken here. So it puzzles people, why do they do this? But it turns out it requires calculus 2 to answer this, calculus 1 to answer this actually. So then 0.2 to the 0.2 power. So 0.2 to the 0.2 power, that's 0.7247. 0.1 to the 0.1 power is equal to, see, it's actually number is going back up. So it's going down, going down, going down, going down, going down, going down, going back up, which is kind of like you feel like the math is broken. So 0.79432. Now we're going to go to 0.1 to the 0.01 equal to 0.9549, 0.00001, to 0.000140, so 0.00001 to the 0.00001 is 0.99988. So you see like this number is going faster, 72 to 79, and from here it's going to 95. You say maybe if I go small enough, it's going past 1. But it turns out a plateau, well, the plateau is going to near to that number. It's actually going to roughly, if I would do 0.0000001 to the 0.000000001, then that would be a 0.99999999793. It's roughly close to 1. If I build enough zeros, some calculators actually give you 1. So some calculator, if you give it 0 to the 0 power, that's actually going to give you something called domain error. So obviously that cannot work. So why does the teacher lie to me? 0 to the 0 power is called indeterminate. So you cannot get an answer, but you can use this process called limit approach. A limit approach can get to a number so close. So remember, this is almost 0, this is almost 0, so we can say safe to assume that 0 to the 0 power is probably more likely 1, but the calculator is still going to show you don't know. But your teacher is going to tell you anything to the 0 power 1, but you should ask, what about 0 to the 0 power? But 0 power to the 0 power is actually practically almost 1. So we can assume that's 1. Okay, so that's interesting. Now let's get down to the next thing is this is the 0 power rule, negative exponent rules. So we're talking about 0 power rule. We just spent a lot of time doing this to show you what math works. But we're going to show you what happened with negative exponent rule. So what if I have 2 to the negative 1 power? Well, we're still following the same pattern, which is 4, 3, 2, 1, 0 to negative 1. So we're going to go down this. So we're going to times 1/2. So it'll be 1/2. So it turns out it's like this. 2 to the negative 1 power is going to switch from numerator to denominator, becomes positive. So it's 1/2. 2 to the negative 2 power is going to times 1/2 again. So 1/2 times 1/2 is 1 to 2 squared. So you see that if we change that number to here with different color, then you see that is changing from negative 2 to positive 2, but changing from numerator to denominator, keep the exact same base. Now you have to understand they prefer to be positive exponents, and that's something that they really, really prefer. Okay, so hopefully that answers a lot of questions for you that you have from Algebra 1 and Algebra 2, why the answer is this way. Now let's go into like the more heavier side, but we're going to stop right here because we're going to make its own video for this one. So we're going to stop right here for the exponential rule because that's the actual exponential rule, and we're going to talk about this one with the second video about exponential rules. So any question about this? So I'm asking for nobody actually. So now, if you have a to the n to the a to the n power, that's just equal to a to the m times n. Okay, not x. So, but some people say I don't like times, I like a dot, which is fine. So why is that important? 2 to the 2 power to the 5th power. So I can rewrite this. But this is a lot of work. I really don't like this. This must be an easy way to do this. They are the same base, multiplied by 5 times. That's going to give me 2 to the 2 plus 2 plus 2 plus 2 plus 2 using the product rule. So it's going to be 10th power. Or I can do this, 2 to the 2 power times 5. Instead of writing out loud, it's 2 times 5. That's equal to 2 to the 10th power, which is short. And everything. And that's the exponential rule for introductions. So we're going to talk about this rule next.